Welcome to Sleepy Science Channel, where the vast mysteries of the universe unfold gently in the darkness, like distant stars emerging as twilight deepens. I'm here to guide you on a peaceful journey through one of the cosmos' most fascinating and serene phenomena, neutron stars. These remarkable celestial objects, born from the quiet transformation of dying suns, hold within their dense hearts some of the universe's most beautiful secrets. As you settle into comfort, let your breathing slow to match the rhythm of cosmic time itself. Feel yourself becoming weightless, drifting through the infinite expanse of space where neutron stars spin in their eternal dance, sending gentle pulses of light across the galaxy like cosmic lighthouses guiding travelers home. Tonight, we'll explore 100 fascinating facts about these stellar remnants, each revelation as soothing as starlight on still water. Allow your mind to wander freely among these distant suns, compressed into spheres smaller than cities, yet containing more mass than our own Sunday. There's something deeply peaceful about contemplating these ancient objects, spinning quietly in space for billions of years, their stories written in the language of physics and poetry combined. If you find this journey relaxing, a gentle like helps other cosmic travelers discover these peaceful facts. And subscribing ensures you'll never miss our next voyage into the serene depths of scientific wonder. But for now, simply rest, breathe deeply, and let yourself be carried away on gentle waves of cosmic knowledge. Let us begin our quiet exploration of the neutron star's beautiful mysteries. Chapter 1: Birth from Stellar Death. Neutron stars are born from the gentle collapse of massive stars, typically those 8 to 30 times more massive than our Sun. When these stellar giants reach the end of their long lives, having burned through millions of years of nuclear fuel, they undergo a transformation as peaceful as it is profound. The star's core, no longer able to sustain the outward pressure of fusion reactions, surrenders to gravity's embrace. In less than a second, the core collapses from the size of Earth to a sphere barely 12 miles across, creating one of nature's most extraordinary objects. Picture this cosmic metamorphosis unfolding in the deep silence of space. The massive star, having shone steadily for millions of years, begins its final, quiet journey. As the nuclear fires in its core dim and fade, gravity takes hold with gentle insistence. The collapse happens so swiftly that if you could witness it from a safe distance, the transformation would appear almost instantaneous, a stellar giant becoming a neutron star in the span of a single heartbeat. During this collapse, protons and electrons are compressed together so tightly that they merge to form neutrons. This process, called neutronization, transforms ordinary matter into something far more exotic. Imagine taking all the empty space within atoms, the vast distances between nucleus and electrons, and compressing it away entirely. What remains is a material so dense that a teaspoon would weigh as much as Mount Everest, composed almost entirely of neutrons packed together like cosmic pearls. The pressure during this transformation exceeds anything we can truly comprehend. It's as if the entire weight of all Earth's mountains were focused on a single grain of sand, yet somehow that grain of sand not only survives but becomes something magnificent. The neutrons, forced into proximity beyond their natural preference, create a new state of matter that exists nowhere else in the universe except in these stellar remnants. The outer layers of the original star are expelled in a supernova explosion, while the core becomes a neutron star. This explosion, despite its violent-sounding name, serves as a gentle farewell from the dying star. The outer shells, enriched with heavy elements forged in the star's nuclear furnace over millions of years, drift outward into space at thousands of miles per second. These expelled materials will eventually seed new star formation, carrying carbon, oxygen, iron, and other elements essential for planets and life itself. Even now, as you rest comfortably, the light from ancient supernovae continues its journey across the cosmos. Some of the elements in your body, the calcium in your bones, the iron in your blood, were forged in the heart of a massive star and scattered into space during its gentle transformation into a neutron star. You are, quite literally, made of stardust from these cosmic events that occurred billions of years ago. The entire collapse process releases more energy in 10 seconds than our Sun will produce in its entire 10 billion-year lifetime. Yet despite this enormous energy release, the process has a serene quality when viewed from the perspective of cosmic time. The energy radiates outward as neutrinos, ghost-like particles that barely interact with matter, carrying away the thermal energy of the collapsing core. These neutrinos stream through space and time, occasionally passing through your body as you sleep, connecting you to the ancient stellar deaths that created the neutron stars we'll explore tonight. Not all massive stars become neutron stars. Those above approximately 30 solar masses collapse directly into black holes. There's something beautifully precise about this cosmic selection process. The universe has its own gentle way of determining which stellar cores will become neutron stars, and which will disappear entirely behind event horizons. It's as if nature has drawn an invisible line in space, beyond which even neutron degeneracy pressure cannot halt the inexorable pull of gravity. The first neutron star was theorized in 1934 by Walter Baade and Fritz Zwicky, just 2 years after the neutron itself was discovered. These visionary astronomers, working with little more than mathematics and imagination, predicted the existence of these exotic objects decades before any would be observed. They understood that the universe must contain stellar remnants so dense that atomic structure itself would be fundamentally altered. Their quiet genius allowed humanity to glimpse the neutron star's existence long before we had the technology to detect their gentle signals. Neutron stars represent one of the most extreme states of matter that we know can exist in the universe. They exist at the boundary between ordinary matter and the exotic physics of black holes. In their cores, matter reaches densities where the normal rules of atomic structure no longer apply, where neutrons themselves might break down into their constituent quarks. They are cosmic laboratories where the fundamental forces of nature play out dramas we can barely imagine. The typical neutron star contains about 1.4 times the mass of our Sun compressed into a sphere, only 12 miles in diameter. To visualize this incredible density, imagine taking our entire Sun, which could fit over 1 million Earths inside it, and compressing it into a ball so small you could drive across it in less than 20 minutes. The surface gravity would be so intense that a single sugar cube would weigh as much as all the world's automobiles combined. As we drift deeper into our exploration, let your mind rest on the profound beauty of these stellar transformations. Somewhere in the distance, in galaxies far beyond our own, massive stars are quietly beginning their final collapse, creating new neutron stars that will spin in darkness for billions of years to come. Even now, these cosmic lighthouses are being born from stellar death, ready to pulse their gentle signals across the cosmos for eons yet to come. Chapter 2: Cities in Space. The Size of Neutron Stars. A typical neutron star has a radius of approximately 6 miles, making it smaller than most major cities. Imagine Manhattan, with all its towering skyscrapers and bustling streets, compressed into a perfect sphere. The neutron star would fit comfortably within this urban landscape, yet contain more matter than our entire Sunday. This extraordinary compactness makes neutron stars among the smallest yet most massive objects in the universe, cosmic cities where the buildings are made of pure neutron matter. Picture yourself floating high above such a stellar remnant, looking down at its smooth, impossibly dense surface. The horizon would curve away sharply in all directions, the entire circumference visible in a single glance. You could walk around the entire neutron star in less time than it takes to stroll through Central Park, yet you'd be traversing the surface of an object containing 500,000 Earths worth of matter, compressed into that tiny sphere. The surface area of a neutron star is roughly equivalent to that of a large metropolitan area, about 450 square miles. This means the entire surface of this stellar remnant would fit within the boundaries of Los Angeles or London. Yet this small patch of cosmic real estate contains more gravitational influence than objects millions of times larger. Every square inch of this surface pulls with a force of 100 billion Earth gravities, creating a gentle but inexorable attraction that bends space-time itself. If Earth were compressed to neutron star density, it would have a diameter of only 300 feet, about the length of a football field. Our entire planet, with its vast oceans, towering mountains, and deep valleys, would become a sphere you could walk across in just a few minutes. All of Earth's mass, its iron core, rocky mantle, and delicate atmosphere, would be compressed into neutron matter so dense that the familiar concepts of rocks, water, and air would simply cease to exist. The density of neutron star matter is approximately 100 trillion times greater than water. To truly appreciate this incredible density, imagine taking a drop of water and somehow packing 100 trillion identical drops into that same tiny space. The atoms themselves would be crushed out of existence there. Electrons and protons merged into an ocean of pure neutrons. This is matter in a state so exotic that it exists nowhere else in the universe except in these stellar remnants and perhaps in the hearts of the most massive atomic nuclei. A sugar cube-sized piece of neutron star material would weigh approximately 100 million tons on Earth. This tiny morsel of stellar matter would outweigh all the automobiles ever manufactured by humanity combined. Even a single grain of neutron star sand would be too heavy for any crane on Earth to lift. Yet in its natural environment, this incredibly dense matter exists in perfect equilibrium, held together by gravity and supported by the quantum pressure of closely packed neutrons. The mass of a neutron star is typically between 1.1 and 2.3 times the mass of our Sun. This represents a remarkable consistency in nature's stellar recycling program. Despite the chaotic violence of stellar collapse and supernova explosions, the resulting neutron stars fall within this narrow range of masses with beautiful precision. It's as if the universe has a preferred recipe for these exotic objects, creating them with just the right amount of matter to remain stable for billions of years. The escape velocity from a neutron star surface is approximately 100,000 miles per second, about 1/3 the speed of light. This means that to leave the surface of a neutron star, an object would need to travel at speeds that approach the fundamental speed limit of the universe itself. Light itself struggles to escape from these dense objects, redshifting as it climbs out of the intense gravitational field. Even photons, massless as they are slowed by the curvature of space-time around these cosmic cities. Despite their incredible density, neutron stars have remarkably smooth surfaces. The immense gravity of these objects acts like a cosmic steamroller, flattening any surface irregularities to heights of less than a few millimeters. Where Earth has mountains reaching miles into the sky and ocean trenches plunging miles below sea level, neutron star surfaces are smoother than a billiard ball. The largest possible mountain on a neutron star would be barely tall enough to stub your toe on. The volume of a neutron star is roughly equivalent to a sphere 12 miles in diameter, similar to the Size of Manhattan Island. You could fit this entire stellar remnant within the boundaries of New York, city's most famous borough, with room to spare for the surrounding boroughs as well. Yet this compact, cosmic city contains gravitational fields so intense that they would tear apart any normal matter that ventured too close, creating gentle tidal forces that could stretch and compress objects into cosmic spaghetti. Neutron stars are so dense that their centers may contain matter in states unknown to terrestrial physics. At the very core of these objects, pressures become so extreme that even neutrons themselves might break down into their constituent quarks, creating a form of matter called quark soup. Scientists can only speculate about the conditions at these depths, where the fundamental particles of matter exist, in states that cannot be replicated in any Earth-based laboratory. As you contemplate these remarkable size comparisons, let your mind drift through the cosmic perspective of scale. Somewhere in the quiet darkness of space, neutron stars no larger than cities continue their ancient rotations, each one a monument to the incredible compressive power of gravity. Over vast stretches of time, these stellar remnants will continue their patient existence, spinning slowly in the cosmic deep, their city-sized forms containing mysteries we're only beginning to understand. Even now, as you rest peacefully, radio telescopes around the world are detecting the gentle pulses from these distant cosmic cities, their signals crossing thousands of years of space to reach our receivers with clockwork precision, like distant lighthouses sending their beams across an ocean of stars. Chapter 3. The Magnetic Kingdom. Neutron stars possess magnetic fields that are typically 100 million to 1 trillion times stronger than Earth's magnetic field. To appreciate this incredible strength, imagine Earth's gentle magnetic field, the invisible force that guides compass needles and creates the beautiful aurora, amplified to almost unimaginable intensity. These stellar remnants exist within their own magnetic kingdoms, surrounded by fields so powerful they would be lethal to any ordinary matter that ventured too close, yet so far away that they pose no threat, existing only as objects of quiet wonder. Picture these magnetic fields as invisible sculptures carved from pure energy, extending far into space. Around each neutron star, they create vast, three-dimensional architectures that channel and direct charged particles, building cathedrals of magnetic force that dwarf any structure humanity has ever conceived. These fields pulse and rotate with the neutron star itself, sweeping through space like cosmic searchlights, their influence extending millions of miles from the tiny stellar core. The magnetic field of a neutron star could erase every credit card on Earth from a distance of 600 miles. This seemingly mundane comparison reveals the awesome scope of these magnetic forces. What we consider powerful magnetic fields on Earth, the kind that can lift automobiles or guide high-speed trains, are utterly insignificant compared to the magnetic kingdoms that surround these stellar remnants. Even at distances where the neutron star would appear as nothing more than a dim point of light, its magnetic influence would completely overwhelm any magnetic technology we possess. These intense magnetic fields are generated by the rapid rotation of the neutron star's highly conductive interior. Like a cosmic dynamo spinning in the depths of space, the neutron star's rotation drags its magnetic field lines around with it, creating electrical currents that flow through the dense neutron matter. This process, called the dynamo effect, transforms the kinetic energy of rotation into magnetic energy, building fields of incredible strength that can persist for millions of years. Neutron star magnetic fields accelerate charged particles to nearly the speed of light. Within the magnetic kingdom surrounding each neutron star, protons and electrons are caught up in the field lines and accelerated to tremendous velocities. These particles spiral along the magnetic field lines like cosmic roller coasters, gaining energy as they travel through the curved paths imposed by the magnetic force. The result is a steady stream of high-energy particles flowing away from the neutron star's magnetic poles. The strongest magnetic fields around neutron stars can actually alter the shape of atoms themselves. In these extreme environments, the fundamental structure of matter begins to change. Atoms become elongated and distorted, stretched into cigar-like shapes by the overwhelming magnetic forces. Even the vacuum of space itself becomes polarized, taking on properties more akin to a crystal than empty nothingness. These are conditions so extreme that they exist nowhere else in the universe. Charged particles trapped in neutron star magnetospheres create beautiful streams of radiation. Like cosmic aurora that never fade, these particles paint streams of light across the electromagnetic spectrum as they spiral through the magnetic field lines. The neutron star becomes surrounded by a glowing magnetosphere, invisible to the naked eye but brilliant when viewed through radio telescopes and X-ray detectors. These gentle streams of radiation carry information about the neutron star's magnetic field across thousands of light-years of space. The magnetic field lines around neutron stars can extend millions of miles into space. These invisible threads of magnetic force create vast, three-dimensional structures that dwarf the neutron star itself. Like the spokes of an enormous wheel, the field lines radiate outward from the stellar remnant, creating a magnetic architecture that spans distances comparable to the orbit of Mercury around our Sun. Within this extended magnetic kingdom, the neutron star's influence shapes the behavior of any matter or radiation that passes nearby. Some neutron stars, called magnetars, have magnetic fields up to 1,000 times stronger than typical neutron stars. These rare objects exist at the very extreme of what matter can withstand. Their magnetic fields are so intense that they can crack the neutron star's crust like cosmic earthquakes, releasing bursts of energy that briefly outshine entire galaxies. Yet even these violent-sounding events occur on timescales so long and at distances so vast that they appear to us as nothing more than gentle flickers in our most sensitive detectors. The decay of neutron star magnetic fields over millions of years provides energy for continued rotation. Like cosmic batteries slowly discharging their stored energy, neutron stars gradually lose their magnetic strength over vast periods of time. This process happens so slowly that a neutron star's magnetic field remains virtually constant for millions of human lifetimes. The energy released by this gradual magnetic decay helps power the neutron star's rotation and the emission of radiation, creating a gentle cosmic engine that operates for eons. Magnetic field lines around neutron stars can reconnect and snap like rubber bands, releasing tremendous bursts of energy. When these field lines become tangled and twisted by the neutron star's rotation, they occasionally reconfigure themselves in explosive events called magnetic reconnection. These cosmic snaps release as much energy as humanity uses in thousands of years, yet they occur so far away and so briefly that they appear to us as mere blips in our radio receivers, like gentle whispers carried across an ocean of stars. As you drift deeper into sleep, imagine yourself floating through these invisible magnetic kingdoms, feeling the gentle pull of forces beyond ordinary comprehension. Long ago, when these neutron stars were newly formed, their magnetic fields were even stronger, creating spectacular displays of cosmic electricity that illuminated the surrounding space like permanent lightning storms, now faded to a gentle glow that we can detect only with our most sensitive instruments. In the quiet darkness of space, these magnetic fields continue their ancient dance, invisible sculptures of pure energy that will persist long after our own sun has grown dim and cold, monuments to the incredible forces that govern the cosmos at its most extreme scales. Chapter 4: spinning lighthouses of the cosmos. Neutron stars can rotate at incredible speeds, with some spinning up to 700 times per second. Imagine a cosmic top the size of a city, spinning so fast that a point on its equator travels at nearly 20% the speed of light. This is the reality of neutron star rotation, where conservation of angular momentum transforms the slow, stately rotation of a massive star into the furious spinning of its compact remnant. The neutron star spins with such precision that it makes the most accurate atomic clocks seem sluggish. By comparison, picture this cosmic ballet unfolding in the depths of space. As the original star collapsed, its rotation rate increased dramatically, like an ice skater pulling in her arms during a spin. The massive star that once rotated perhaps once every few weeks became a neutron star spinning hundreds of times each second, its rotation locked in by the fundamental laws of physics into a dance that will continue for millions of years. These rapidly spinning neutron stars are called pulsars because they emit beams of radiation from their magnetic poles. Like cosmic lighthouses sweeping their beams across a dark ocean, pulsars send concentrated streams of radio waves, X-rays, and gamma rays into space. As the neutron star rotates, these beams sweep through space in precise, predictable patterns. When Earth happens to lie in the path of these beams, we detect regular pulses of radiation, as rhythmic and reliable as a cosmic metronome. The lighthouse analogy captures something beautiful about these stellar remnants. Just as maritime lighthouses have guided ships safely to harbor for centuries, pulsars serve as navigational beacons for spacecraft and provide astronomers with cosmic reference points of extraordinary precision. Their pulses arrive at Earth with such regularity that they rival atomic clocks in their accuracy, creating celestial timepieces that tick with the fundamental rhythms of the universe itself. The fastest spinning neutron star discovered rotates 716 times per second. This remarkable object, designated PSR J1748-2446 AD, spins so rapidly that it defies easy comprehension. In the time it takes you to blink your eye, this neutron star completes more than 200 full rotations. The fact that it can maintain such incredible rotation without flying apart is a testament to the incredible strength of neutron matter and the precision of gravitational forces that hold these objects together. Pulsar timing is so precise that it rivals atomic clocks in accuracy. The radio pulses from these cosmic lighthouses arrive at Earth with such regularity that astronomers can predict their arrival times to within microseconds, sometimes over periods of many years. This extraordinary precision makes pulsars valuable tools for testing fundamental physics, from Einstein's theory of relativity to the search for gravitational waves rippling through spacetime itself. The rotation of neutron stars gradually slows down over millions of years due to energy loss. Like cosmic wind-up toys slowly running down, pulsars lose energy through the emission of radiation and the drag of their magnetic fields. This process occurs so gradually that a pulsar's rotation period might increase by only a few nanoseconds per year. Over vast stretches of cosmic time, these energetic young pulsars will eventually slow to more sedate rotation rates, their lighthouse beams growing dimmer as they age. Some pulsars are members of binary systems, where they can actually spin up due to matter falling onto them from a companion star. These rejuvenated pulsars, called millisecond pulsars, have been spun up to incredible rotation rates by accreting matter from nearby stellar companions. The falling matter transfers its angular momentum to the neutron star, causing it to spin faster and faster, like a cosmic carnival ride being pushed by an invisible hand. This process can continue for millions of years, creating some of the most rapidly rotating objects in the universe. The emission beams from pulsars are thought to originate from the neutron star's magnetic poles. Charged particles accelerated by the intense magnetic field create streams of radiation that emerge from regions near the magnetic poles. Much like the aurora on Earth, emerge near our planet's magnetic poles. These beams are highly collimated, creating narrow cones of radiation that sweep through space like cosmic searchlights, visible only when they happen to point in Earth's direction. Not all neutron stars are observed as pulsars. We can only detect those whose beams happen to sweep across Earth. For every pulsar we observe, there are likely several more neutron stars whose emission beams never point toward our planet. These invisible lighthouses continue their cosmic dance in the darkness, their beams sweeping across other regions of space, perhaps illuminating worlds in distant star systems that we will never know exist. Pulsars can be used as natural laboratories for studying extreme physics. The incredible densities, magnetic fields, and rotation rates of these objects create conditions that cannot be replicated in any terrestrial laboratory. By studying pulsar radiation, scientists can probe the behavior of matter under extreme conditions, test theories of gravity, and explore the fundamental properties of space and time itself. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and initially thought to be a signal from extraterrestrial intelligence. The incredibly regular pulses, arriving every 1.337 seconds with clockwork precision, was so artificial seeming that the discovery team initially called the source LGM-1 for Little Green Men. Only after finding several more pulsars did astronomers realize they had discovered a new type of cosmic object, opening an entirely new window onto the extreme physics of neutron stars. Pulsar glitches occur when the neutron star's crust suddenly readjusts, causing an instantaneous increase in rotation speed. These cosmic hiccups happen when the incredible stresses within the neutron star's crust cause it to crack and settle into a new configuration. The sudden change can cause the pulsar to spin slightly faster, like a spinning top that suddenly becomes better balanced. These glitches provide insights into the internal structure of neutron stars and the exotic behavior of matter under extreme conditions. As you rest quietly, imagine the gentle sweep of pulsar beams across the cosmos, invisible lighthouses, marking time with incredible precision in the vast darkness of space. Somewhere in the distance, hundreds of these cosmic timepieces continue their ancient rotations, their beams sweeping across empty space and distant worlds, carrying information about the fundamental laws of physics across thousands of light-years of cosmic ocean. Even now, radio telescopes around the world are listening to these gentle cosmic voices, recording their precise timing and using their signals to map the structure of space itself, transforming the universe into a vast clockwork mechanism where neutron stars serve as the most accurate timekeepers ever discovered. Chapter 5: The Dance of Binary Stars. Approximately half of all neutron stars exist in binary systems, locked in gravitational dances with companion stars. These cosmic partnerships represent some of the universe's most beautiful and complex relationships, where two stellar objects orbit around their common center of mass in elegant elliptical paths. The gravitational forces between them create a celestial choreography that has been ongoing for millions of years, each partner influencing the other's evolution in ways both subtle and profound. Picture these binary systems as cosmic waltzes performed on scales almost too vast to comprehend. The neutron star and its companion sweep through space in graceful arcs, sometimes approaching within a few 100,000 miles of each other, sometimes separating by distances greater than the orbit of Earth around the Sun. Their dance continues with mathematical precision, governed by the same gravitational forces that keep planets in orbit around stars. In many binary systems, matter streams from the companion star onto the neutron star in brilliant accretion disks. When the companion star is large enough and close enough, the neutron star's immense gravity can pull material away from the normal star's outer layers. This stolen matter doesn't fall directly onto the neutron star, but instead forms a swirling disk of hot gas that spirals inward like cosmic water circling a drain. The friction within this disk heats the material to millions of degrees, causing it to glow brilliantly in X-rays. These accretion disks are among the most efficient energy producers in the universe, converting matter into energy with far greater efficiency than even nuclear fusion. As the hot gas spirals inward, it releases gravitational potential energy that illuminates the entire binary system, creating cosmic lighthouses that can be seen across vast distances. The process is gentle yet inexorable, like a cosmic river flowing slowly but steadily from one star to another. Binary neutron star systems lose energy through gravitational wave radiation, causing their orbits to decay slowly. Einstein's theory of general relativity predicted that accelerating masses would create ripples in the fabric of spacetime itself, carrying away energy in the form of gravitational waves. In binary neutron star systems, these waves are continuously generated as the two massive objects orbit each other, gradually draining energy from the system and causing the neutron stars to spiral slowly inward toward each other. This process occurs over millions of years, so slowly that the orbital decay would be imperceptible to human observation over many lifetimes. Yet with precise timing measurements of pulsar signals, astronomers have detected this gradual decay, providing the first indirect evidence for gravitational waves decades before they were directly detected by instruments on Earth. The Hulse-Taylor pulsar system provided the first indirect evidence for gravitational waves. This remarkable binary system, discovered in 1974, consists of two neutron stars orbiting each other every 7.75 hours. By precisely timing the pulsar's radio signals over many years, astronomers Russell Hulse and Joseph Taylor were able to measure the gradual decay of the orbit with exquisite precision. The rate of decay matched Einstein's predictions for energy loss through gravitational wave radiation exactly, earning them the Nobel Prize in Physics and confirming one of the most subtle predictions of general relativity. The beauty of this discovery lies in its elegant simplicity. By using the neutron star itself as a cosmic clock, astronomers could detect changes in orbital motion so small they would be completely unnoticeable by any other means. The pulsar's radio beacon, sweeping across Earth hundreds of times per second, served as a precision timing device that revealed the slow dance of gravitational waves carrying energy away into the cosmos. Some binary systems contain a neutron star and a normal star, creating X-ray binaries. In these partnerships, the normal star serves as a gentle donor, gradually feeding material to its neutron star companion through stellar winds or direct mass transfer. As this material falls toward the neutron star, it heats up to temperatures of millions of degrees, emitting brilliant X-rays that can outshine entire galaxies. For brief periods, these X-ray binaries pulse and flicker as material flows between the two stars, creating cosmic light shows visible to our X-ray telescopes. Millisecond pulsars are often found in binary systems where they have been recycled by accretion. These ancient neutron stars have been given a second lease on life by their companion stars. Over millions of years, material falling onto the neutron star from its companion gradually spins it up to incredible rotation rates, transforming what was once a slowly rotating, dim neutron star into a rapidly spinning cosmic lighthouse. This recycling process can accelerate neutron stars to rotation periods of just a few milliseconds, making them some of the fastest spinning objects in the universe. Binary neutron star mergers are among the most energetic events in the universe. When two neutron stars finally spiral together after millions of years of orbital decay, they create cataclysmic collisions that briefly outshine entire galaxies. These kilonova explosions forge heavy elements like gold and platinum in their nuclear fires, scattering them into space to be incorporated into future generations of stars and planets. The collision also sends gravitational waves rippling through spacetime at the speed of light, carrying the news of this cosmic event to distant observers. The orbital periods of neutron star binaries can range from minutes to years. Some neutron star pairs orbit each other so closely that they complete an orbit in less than 11 minutes, whirling around each other at incredible speeds in a cosmic dance that will inevitably end in merger. Others maintain more leisurely orbits, taking months or even years to complete a single revolution, their gravitational embrace so gentle that they may continue their dance for billions of years before finally coming together. Eclipsing binary pulsars provide unique opportunities to study neutron star properties. When the orbit of a binary system is aligned just right, the companion star periodically passes in front of the pulsar, as seen from Earth, creating regular eclipses of the pulsar's radio signal. These eclipses reveal details about the companion star's atmosphere and the space between the two objects, providing astronomers with information about plasma densities, magnetic fields, and the structure of stellar winds. Some neutron stars in binary systems experience thermonuclear explosions on their surfaces. When hydrogen-rich material from a companion star accumulates on the neutron star's surface, it can undergo sudden thermonuclear burning in events called Type 1 X-ray bursts. These explosions are visible as brief, intense flashes of X-rays that can increase the system's brightness by factors of thousands for a few seconds or minutes. The neutron star's surface becomes momentarily as hot as the core of a normal star, then gradually cools back to its normal temperature. Wide binary systems with neutron stars can persist for billions of years. When neutron stars have companions at large distances, sometimes separated by hundreds of times the Earth-Sun distance, the gravitational wave radiation is so weak that orbital decay occurs on timescales longer than the age of the universe. These wide binaries will continue their stately dance essentially forever, two stellar remnants slowly orbiting through the cosmic deep, their gravitational partnership outlasting the evolution of entire galaxies. As you drift deeper into peaceful sleep, imagine these cosmic partnerships continuing their ancient dances in the darkness of space. Over vast stretches of time, binary neutron stars spiral closer together in gravitational embraces that began when the universe was young. Their orbital motion creates gentle ripples in spacetime itself, gravitational waves that carry away energy with infinite patience, bringing these stellar partners slowly but inevitably together in cosmic unions that will reshape the very fabric of space and time. Even now, somewhere in a distant galaxy, two neutron stars are completing what may be their final orbits around each other, their gravitational waves racing toward Earth at the speed of light, carrying the message of their impending merger across millions of years of space, destined to arrive at our gravitational wave detectors as whispers from the deepest reaches of the cosmic ocean. Chapter 6. Magnetars, the gentle giants with fierce fields. Magnetars are a special class of neutron stars with magnetic fields up to 1,000 times stronger than typical neutron stars. These remarkable objects exist at the very edge of what physics tells us is possible. Their magnetic fields so intense they approach the quantum critical field where even empty space begins to behave like a material substance. Yet despite their fearsome-sounding name, magnetars spend most of their time in quiet contemplation, their incredible magnetic energy stored within their crystalline crusts, like cosmic batteries waiting patiently in the darkness. Picture these magnetic giants floating serenely in space, their invisible field lines extending millions of miles in all directions, creating three-dimensional sculptures of pure magnetic force more complex than any human artwork. These fields are so strong they could strip the information from every credit card on Earth from a distance of 100,000 miles, yet they exist so far away that they pose no threat to us, serving only as objects of wonder and scientific curiosity. The magnetic field of a magnetar is approximately 10 to the power of 15 Gauss, strong enough to be lethal at a distance of 600 miles. To put this incredible strength in perspective, Earth's magnetic field measures just half a Gauss, while the strongest magnetic fields ever created in laboratories barely reach 45 Tesla, or 450,000 Gauss. A magnetar's field is so powerful it would kill any living thing through magnetic field induced disruption of neural activity and the molecular bonds that hold biological tissues together, yet this destruction would occur gently, without violence, simply through the overwhelming presence of organized magnetic force. These intense magnetic fields are thought to be generated during the neutron star's formation in particularly energetic core collapse supernovae. When certain massive stars collapse, the dynamo effect that generates the magnetic field becomes extraordinarily efficient, perhaps amplified by rapid rotation and convective motion in the newly formed neutron star. The magnetic field becomes frozen into the ultradense neutron matter, preserved like ancient ice in a cosmic glacier, maintaining its incredible strength for millions of years. Magnetar starquakes can crack the neutron star's crust and reorganize its magnetic field. Immense magnetic pressure within a magnetar occasionally overcomes the structural integrity of the neutron star's crystalline crust, causing it to crack and shift like tectonic plates on Earth. These cosmic earthquakes release more energy than our Sun produces in 100,000 years, yet they occur so far away that they reach us only as brief gamma-ray bursts lasting fractions of a second, gentle flickers in our most sensitive space-based detectors. During these starquakes, the magnetic field lines snap and reconnect like cosmic rubber bands, releasing tremendous bursts of high-energy radiation. The neutron star's surface, harder than any diamond, fractures under magnetic stresses that exceed the strength of steel by factors of billions. Yet even these violent-sounding events have a certain cosmic beauty, representing the magnetar's attempt to find a new, more stable configuration for its incredible magnetic energy. The strongest magnetic fields around magnetars can alter the properties of atoms and even empty space itself. In these extreme environments, hydrogen atoms become stretched into elongated cigars, their electron orbitals distorted by magnetic forces. Even the quantum vacuum becomes birefringent, splitting light into different polarizations just like certain crystals do on Earth. The very nature of empty space changes in the presence of such intense magnetic fields, creating conditions that exist nowhere else in the observable universe. Magnetars occasionally produce giant flares that briefly outshine entire galaxies. These rare events, occurring perhaps once every few decades for a typical magnetar, release as much energy in a few tenths of a second as our Sun produces in 250,000 years. The December 27, 2004 flare from magnetar SGR 1806-20 was so intense that it temporarily blinded several space-based gamma-ray detectors and caused measurable changes in Earth's ionosphere, despite occurring 50,000 light-years away. Yet even these incredible outbursts have a fleeting, almost gentle quality when viewed from cosmic perspectives. The intense radiation lasts only seconds, followed by a gradually fading afterglow that may persist for months. The magnetar then returns to its quiet state, conserving its magnetic energy for perhaps another few decades before the next major reorganization of its field structure. Only about 30 magnetars have been identified in our galaxy, making them extremely rare objects. These magnetic giants represent perhaps 1 in 1,000 of all neutron stars, requiring special conditions during their formation to develop such intense magnetic fields. They are cosmic rarities, scattered throughout the Milky Way like hidden gems, most of them discovered only when they produce detectable bursts of high-energy radiation during periods of magnetic activity. Young magnetars are more active, with their burst rate decreasing as they age over thousands of years. Like cosmic fireworks gradually burning out, magnetars slowly exhaust their magnetic energy over millennia. Young magnetars may produce dozens of detectable bursts per year, while older ones may remain quiet for decades between episodes of activity. This gradual decline creates a natural aging process as the magnetar's field slowly decays and its crust settles into increasingly stable configurations. The rotation periods of magnetars are typically longer than those of regular pulsars, usually between 2 and 12 seconds. This slower rotation is likely due to the magnetic braking effect of their incredibly strong fields. The magnetic field lines extend far into space, interacting with the sparse interstellar medium and gradually slowing the neutron star's rotation through electromagnetic friction. This creates a gentle cosmic brake that operates over thousands of years, gradually transforming rapidly spinning neutron stars into slowly rotating magnetic giants. Magnetar fields decay over timescales of thousands to millions of years. Like cosmic batteries slowly discharging, magnetars gradually lose their magnetic energy through various processes including ambipolar diffusion and magnetic reconnection events. The incredibly strong fields that make magnetars so distinctive are temporary features on cosmic timescales, destined to fade away as the magnetar evolves into a more ordinary neutron star with a weaker magnetic field. As you rest in the quiet darkness, imagine these magnetic giants spinning slowly in the depths of space. Their invisible force fields creating vast sculptures of organized energy that will persist for thousands of human lifetimes. Long ago, when these magnetars were first formed, their magnetic fields were even stronger, creating spectacular displays of high-energy radiation that illuminated their surrounding regions. Like cosmic fireworks. Now, in their more mature phase, they rest quietly most of the time, conserving their magnetic energy while slowly rotating through the cosmic night. Even now, somewhere in our galaxy, a magnetar may be experiencing a gentle reorganization of its magnetic field, its crystalline crust cracking under forces beyond human comprehension, releasing a brief flash of gamma rays that will race across space for thousands of years before reaching our detectors as a whisper-soft reminder of the incredible forces that shape the universe on its grandest scales. Chapter 7: Neutron Star Collisions. Cosmic Alchemy. When two neutron stars spiral together and merge, they create kilonovae, explosions that forge heavy elements and briefly outshine entire galaxies. These cosmic collisions represent nature's most powerful alchemical laboratories, where the fundamental building blocks of matter are transformed under conditions of unimaginable temperature and pressure. In the space of milliseconds, neutron star mergers create more gold than our sun could produce in billions of years, scattering these precious elements into space to eventually become part of future planets and perhaps even living beings. Picture this ultimate cosmic dance reaching its crescendo as two city-sized objects, each containing more mass than our sun, spiral together at speeds approaching that of light itself. The merger happens so quickly that the entire event is over in less time than it takes to blink an eye, yet the effects ripple outward through space and time, creating gravitational waves that carry news of the collision across billions of light-years of cosmic ocean. The collision of two neutron stars releases as much energy as 10 billion suns shining for an entire year. This incredible energy output makes neutron star mergers among the most luminous events in the universe, visible across cosmic distances that span billions of light-years. Yet despite this enormous Energy release. The process has an almost gentle quality when viewed from the perspective of cosmic time, unfolding over milliseconds in a universe that measures its evolution in billions of years. The energy emerges in multiple forms: gravitational waves that ripple through spacetime itself, gamma ray bursts that race outward at the speed of light, and the thermal glow of newly synthesized heavy elements expanding into space like an enormous cosmic firework. Each form of energy carries information about the conditions inside the merging neutron stars, providing scientists with unprecedented insights into matter under the most extreme conditions possible. During the merger, temperatures reach 100 billion degrees, about 6,000 times hotter than the core of the Sun. At these incredible temperatures, atomic nuclei break apart and reassemble in rapid fire. Nuclear reactions that synthesize heavy elements through the rapid neutron capture process, or R process. This cosmic nuclear furnace operates for only a few seconds, but in that brief time it produces more heavy elements than could be created by millions of years of stellar nucleosynthesis. Neutron star mergers are responsible for creating approximately half of all elements heavier than iron in the universe. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, all of these heavy elements were forged in the incredible heat and pressure of neutron star collisions that occurred billions of years ago. You are quite literally wearing and using the products of these ancient cosmic catastrophes, carrying within your body atoms that were created in some of the most violent yet beautiful events the universe can produce. The first direct detection of gravitational waves from a neutron star merger occurred on August 17, 2017. This historic event, designated GW 170817, marked the beginning of multi-messenger astronomy, where the same cosmic event was observed through gravitational waves, gamma rays, X-rays, optical light, and radio waves. The gravitational wave signal lasted for about 100 seconds, slowly increasing in frequency as the two neutron stars spiraled closer together, ending abruptly at the moment of merger in what scientists poetically call the chirp. This detection fulfilled Einstein's prediction from over a century earlier that colliding masses would create ripples in spacetime itself. The gravitational waves from this merger traveled for 130 million years across the cosmos, carrying information about the final moments of two neutron stars that died long before complex life appeared on Earth, their message finally reaching our detectors as whispers of cosmic violence transformed into scientific triumph. The optical afterglow from neutron star mergers can remain visible for weeks or months. After the initial burst of gamma rays and gravitational waves, the expanding cloud of ejected material continues to glow as radioactive elements decay and the shock wave interacts with surrounding interstellar material. This kilonova afterglow changes color over time, shifting from blue to red as the expanding material cools, and different elements dominate the emission. Astronomers can analyze this changing spectrum to identify the specific heavy elements created in the merger. Each neutron star merger ejects about 1/100th of a solar mass worth of heavy elements into space. This may seem like a small amount, but when spread across the vast scales of galactic evolution and multiplied by millions of mergers over billions of years, these ejected elements gradually enrich the interstellar medium with the heavy elements necessary for planet formation and ultimately life itself. Every neutron star merger is a cosmic seed spreader, distributing the elements of complexity throughout the universe. The merger process can create short gamma-ray bursts, the most energetic explosions in the universe. When the collision produces a black hole surrounded by an accretion disk, jets of material can be accelerated to nearly the speed of light and focused into narrow beams that shine briefly with the power of trillions of suns. These gamma-ray bursts last only seconds, but they can be detected across billions of light-years, serving as cosmic lighthouses that mark the locations of neutron star mergers throughout the observable universe. Some neutron star mergers may produce magnetars or other exotic neutron star variants. If the total mass of the merging system is below a critical threshold, the collision may produce a new, more massive neutron star rather than a black hole. These merger remnants often have unusual properties: rapid rotation, intense magnetic fields, or unusual compositions that make them cosmic laboratories for studying matter under extreme conditions. The rate of neutron star mergers in our galaxy is estimated at about 1 every 10,000 to 100,000 years. This means that somewhere in the Milky Way, binary neutron star systems are slowly spiraling toward their ultimate embrace, their orbits decaying over millions of years as gravitational waves carry away their orbital energy. Most of these future mergers involve neutron star pairs that formed billions of years ago and have been patiently dancing together ever since, waiting for their moment of cosmic alchemy. Neutron star mergers may also produce exotic matter like strange quarks or create conditions where quarks exist freely outside of normal particles. In the incredible densities and temperatures achieved during collision, the fundamental structure of matter itself may break down, allowing quarks, normally confined within protons and neutrons, to exist as free particles in a quark-gluon plasma. This exotic state of matter existed throughout the universe only in the first microseconds after the Big Bang, recreated briefly in neutron star mergers before cooling back into normal matter. As you drift peacefully toward sleep, imagine these cosmic alchemical laboratories scattered throughout the universe, each one a forge where the elements of complexity are created and distributed into space. Long ago, perhaps 4.5 billion years before Earth formed, neutron star mergers in our region of the galaxy scattered heavy elements into the gas clouds that would eventually collapse to form our solar system, ensuring that rocky planets like Earth would have the chemical complexity necessary for oceans, continents, and ultimately life itself. Even now, gravitational waves from distant neutron star mergers are racing toward Earth at the speed of light, carrying messages from cosmic collisions that occurred when the universe was young, destined to arrive at our detectors as gentle whispers that speak of creation through destruction, of beauty emerging from violence, of the universe's patient work in forging the elements of existence through the most extreme processes nature can devise. Chapter 8. The Interior, a Journey to the Center. The interior of a neutron star exists in layers, each more exotic than the one above it, like cosmic Russian nesting dolls made of increasingly strange matter. As we journey from the surface toward the center of these stellar remnants, we encounter materials that exist nowhere else in the universe, each layer governed by different physical laws as density and pressure increase beyond anything we can replicate on Earth. This descent into the neutron star's heart is a voyage through states of matter so exotic that they challenge our understanding of reality itself. Picture beginning this journey on the neutron star's surface, standing on ground so dense that a teaspoon would weigh as much as Mount Everest, looking down into an abyss where the very concepts of atoms, nuclei, and familiar particles gradually dissolve into something far more mysterious. The surface beneath our feet is smoother than a billiard ball, yet harder than diamond, a crystalline landscape of incredible density stretching in all directions to a horizon only a few miles away. The outermost layer consists of a solid crystalline crust made of atomic nuclei arranged in a lattice structure. This outer crust extends down about half a mile below the surface, containing matter at densities up to 100 million times that of water. Here, familiar elements like iron, nickel, and heavier nuclei exist in a sea of free electrons, but the incredible gravity compresses them into crystal structures unlike anything found on Earth. The nuclei are packed together far more tightly than in normal matter, creating a cosmic crystal that spans the entire outer shell of the neutron star. These crystalline structures have properties that would seem magical if we could somehow examine them directly. They conduct electricity perfectly with zero resistance, making the entire neutron star crust a superconductor on a cosmic scale. The crystal lattice is so perfectly ordered that it would make the finest human-made crystals seem rough and impure by comparison, yet it exists under gravitational pressures that would instantly crush any normal matter. Below the outer crust lies the inner crust, where neutrons begin to drip out of atomic nuclei. Densities approaching that of atomic nuclei themselves, the nuclei become so neutron-rich that they can no longer hold all their neutrons. These excess neutrons drip out and form a superfluid sea that flows freely between the crystalline lattice of remaining nuclei. This neutron superfluid has no viscosity whatsoever. It flows without any friction or resistance, creating currents that could persist for millions of years without dissipating. The transition from outer to inner crust occurs gradually, like a cosmic phase change that spans several hundred meters of depth. As we descend, the nuclei become increasingly neutron-rich and begin to take on exotic shapes. Spheres give way to rods, then to slabs, creating what physicists call nuclear pasta, because of the resemblance to various pasta shapes. These exotic nuclear configurations exist only in the incredibly high-density environment of neutron star interiors. The core of a neutron star consists almost entirely of neutrons in a superfluid state, with a small fraction of protons and electrons. Here, at densities several times that of atomic nuclei, individual neutrons lose their identity as separate particles and merge into a quantum superfluid that behaves more like a single macroscopic quantum object than a collection of individual particles. This neutron superfluid fills the interior of the neutron star, flowing without friction and exhibiting quantum properties on astronomical scales. Within this neutron superfluid, the protons also form a superfluid, and the electrons move as a perfect superconducting fluid. The result is a triple superfluid system: neutron superfluid, proton superfluid, and superconducting electrons, all existing in the same volume but behaving as separate, interpenetrating quantum fluids. This exotic state of matter combines the quantum mechanical properties we normally associate with atomic scale systems with the vast scales of astronomical objects. At the very center of the most massive neutron stars, matter may break down into free quarks. In these innermost regions, where densities may exceed 10 times that of nuclear matter, even neutrons and protons cannot maintain their integrity. The quarks that normally exist confined within these particles may break free, creating a quark-gluon plasma similar to what existed throughout the universe in the first microseconds after the Big Bang. This quark matter would be the most exotic substance in the contemporary universe, a throwback to the fundamental conditions that prevailed when space and time themselves were young. The equation of state for neutron star matter, the relationship between pressure and density, remains one of physics' great unknowns. Scientists can calculate the properties of neutron star matter up to certain densities, but beyond about twice nuclear density, theory becomes uncertain. Different models predict dramatically different behaviors for matter at these extreme densities, from simple neutron fluids to exotic states containing hyperons, kaons, or deconfined quarks. Each possibility would create neutron stars with different maximum masses, different cooling rates, and different gravitational wave signatures. Neutron star interiors may contain the most perfect superfluids and superconductors in the universe. The neutron and proton superfluids in neutron star cores have transition temperatures of millions or even billions of degrees, meaning they remain in their superfluid state throughout the neutron star's lifetime. Similarly, the electrons form superconductors that would maintain perfect electrical conductivity even at temperatures far exceeding those found in stellar cores. These quantum fluids exist on scales of several miles in diameter, making them the largest quantum objects known to exist. The magnetic field within neutron stars may be frozen into the superconducting interior. Like magnetic field lines trapped in a superconducting wire, the neutron star's magnetic field becomes locked into the superconducting core material, unable to move or decay through normal processes. This magnetic flux conservation helps explain why neutron stars can maintain their intense magnetic fields for millions of years, and why magnetic field reorganization during starquakes can cause such dramatic changes in the neutron star's behavior. Temperature gradients within neutron stars create convection patterns in the superfluid interior. Despite being superfluids with zero viscosity, the neutron and proton fluids can still carry heat through convection, creating circulation patterns that span the entire neutron star interior. These convective flows help transport heat from the interior to the surface, contributing to the neutron star's cooling over millions of years. The interaction between convection, rotation, and magnetic fields creates a complex, three-dimensional dance of quantum fluids within each neutron star. Crystalline structures in the neutron star crust can store enormous amounts of elastic energy. The perfect crystal lattice that makes up the neutron star's crust can be twisted and strained by changes in the neutron star's rotation or magnetic field, storing elastic energy like a cosmic spring. When this stored energy is suddenly released during a starquake, it can crack the crust and change the neutron star's rotation rate instantaneously, creating the glitches observed in pulsar timing. The interface between the crust and core may harbor exotic vortex structures. The rotation of the superfluid core creates quantized vortices, tornado-like structures where the superfluid circulates with precisely defined amounts of angular momentum. These vortices interact with the magnetic flux tubes trapped in the superconducting matter, creating a complex three-dimensional array of rotating quantum structures that span the entire neutron star interior. As you descend deeper into sleep, imagine this journey to the center of a neutron star, traveling through layers of matter so exotic they exist nowhere else in the universe. In the quiet darkness of space, these cosmic laboratories continue their patient exploration of fundamental physics, their interiors harboring superfluids and superconductors that surpass any human technology, quantum states that persist on astronomical scales, and forms of matter that may hold keys to understanding the deepest laws governing reality itself. Even now, in neutron star cores throughout the galaxy, triple superfluids flow without friction through crystalline lattices harder than diamond, their quantum properties operating on scales larger than entire cities, creating natural laboratories where the universe experiments with the ultimate limits of matter, energy, and space itself. Chapter 9. Observation and Discovery. The first neutron star was discovered in 1967 by Jocelyn Bell Burnell as a graduate student at Cambridge University. Working with radio telescopes to study quasars, she noticed an unusual signal that appeared as regular pulses every 1.337 seconds, so precise and artificial seeming that the research team initially wondered if they had detected a signal from extraterrestrial intelligence. They playfully called the source LGM-1 for Little Green Men, but soon realized they had discovered something far more extraordinary, a new type of cosmic object that would revolutionize our understanding of stellar evolution and extreme physics. Picture the quiet excitement of that discovery unfolding in the modest radio astronomy lab where chart recorders traced out signals from space onto long rolls of paper. Bell Burnell, examining hundreds of feet of chart recordings by hand, spotted the tiny recurring signals that would change astronomy forever. Her careful attention to detail and persistence in investigating what others might have dismissed as interference led to one of the most important discoveries in modern astrophysics. Neutron stars were actually predicted theoretically in 1934, 33 years before the first one was observed. Just 2 years after the discovery of the neutron itself, astronomers Walter Baade and Fritz Zwicky proposed that stellar collapse could create objects composed almost entirely of neutrons. Their visionary insight, based purely on theoretical physics and astronomical reasoning, imagined these exotic stellar remnants decades before we had the technology to detect them. It was a triumph of human imagination and mathematical understanding over observational limitations. Radio telescopes detect neutron stars through their regular pulses of radio waves, earning them the name pulsars. These cosmic lighthouses sweep beams of radio radiation across space as they rotate, and when Earth happens to lie in the path of these beams, we detect regular pulses that can be timed with extraordinary precision. The radio signals themselves are quite faint, typically requiring dish antennas hundreds of feet in diameter to detect, but their regularity makes them unmistakable once identified. Modern radio telescopes can detect pulsars at distances of thousands of light-years, their signals carrying information about the neutron star's rotation rate, magnetic field strength, and motion through space. Each pulse is like a cosmic telegram, carrying news from these distant stellar remnants across vast expanses of space and time, their messages arriving at Earth with the reliability of atomic clockwork. X-ray observations reveal neutron stars in binary systems through their accretion disks. When neutron stars have stellar companions, material falling from the companion star onto the neutron star creates brilliant X-ray sources that can outshine entire galaxies. These X-ray binaries flicker and pulse as hot gas spirals onto the neutron star's surface, creating lighthouse beacons visible to our space-based X-ray telescopes. The X-ray emission provides information about the neutron star's mass, magnetic field, and the properties of matter under extreme gravitational fields. Gravitational wave detectors like LIGO have opened a new window onto neutron star mergers. These incredibly sensitive instruments can detect the tiny ripples in spacetime created when neutron stars spiral together and merge. The gravitational wave signals from these mergers carry information about the neutron star's masses, spins, and internal structure, providing insights into the equation of state of matter. At nuclear density, each detection is like receiving a message written in the curvature of spacetime itself. The LIGO detectors are marvels of precision engineering, capable of measuring changes in distance smaller than 1/10,000th the width of a proton. When gravitational waves from a distant neutron star merger pass through Earth, they stretch and compress space itself by these tiny amounts, causing laser beams in the detector arms to shift phase by barely detectable amounts. The technology required to make such measurements approaches the fundamental limits imposed by quantum mechanics. Multi-messenger astronomy combines observations from different types of cosmic radiation. The August 17, 2017 neutron star merger GW 170817 was observed through gravitational waves, gamma rays, X-rays, optical light, radio waves, and neutrinos, providing the most complete picture ever obtained of a single cosmic event. Each type of radiation revealed different aspects of the merger process, from the initial gravitational wave chirp through the gamma-ray burst to the slowly fading optical afterglow, powered by radioactive decay of newly synthesized heavy elements. Pulsar timing arrays use collections of precisely timed pulsars as a galaxy-sized gravitational wave detector. By monitoring the arrival times of pulses from dozens of pulsars scattered throughout our region of the galaxy, astronomers can detect the subtle timing changes caused by gravitational waves passing between the pulsars and Earth. This technique is sensitive to gravitational waves with much longer wavelengths than ground-based detectors can observe, potentially revealing the signatures of supermassive black hole mergers or exotic cosmic phenomena from the early universe. Neutron star observations have confirmed many predictions of Einstein's general relativity. The precise timing of binary pulsar orbits has verified gravitational wave emission, gravitational redshift, relativistic precession, and time dilation effects with extraordinary precision. These natural laboratories allow scientists to test fundamental physics under conditions that cannot be replicated in terrestrial experiments, confirming that Einstein's century-old theory remains accurate even in the most extreme gravitational environments known to exist. Fast radio bursts may be linked to magnetars and other neutron star phenomena. These mysterious millisecond duration radio signals from distant galaxies have puzzled astronomers since their discovery in 2007. Recent observations have connected some fast radio bursts to magnetar flares, suggesting that the extreme magnetic fields and sudden energy releases from these neutron stars may create brief but incredibly bright radio signals visible across cosmic distances. Neutron star surface temperatures can be measured through X-ray spectroscopy. Young neutron stars have surface temperatures of about 1 million degrees, gradually cooling over millions of years through neutrino emission and photon radiation. By analyzing the X-ray spectra from neutron star surfaces, astronomers can measure these temperatures and study how neutron stars cool, providing insights into the thermal properties of neutron matter and the role of exotic cooling processes in neutron star interiors. The discovery of millisecond pulsars revealed that neutron stars can be recycled through accretion. These rapidly spinning pulsars, rotating hundreds of times per second, were initially mysterious because their rapid rotation seemed incompatible with their presumed old age. The solution came with the realization that neutron stars in binary systems can be spun up by material falling onto them from companion stars, transforming slowly rotating old neutron stars into rapidly spinning millisecond pulsars through cosmic recycling. Interferometry techniques allow astronomers to measure neutron star sizes with unprecedented precision. By combining observations from multiple telescopes, astronomers can achieve angular resolution fine enough to study details of neutron star surfaces and magnetospheres. Future missions may be able to map surface features on nearby neutron stars, revealing details about their magnetic field structure, surface composition, and thermal emission patterns. As you rest quietly in the darkness, imagine radio telescopes around the world continuing their patient vigil, listening to the gentle voices of pulsars scattered throughout our galaxy. Even now, these cosmic lighthouses are sending their precisely timed signals across thousands of light-years of space, their radio beams sweeping through the cosmic night like distant lighthouse beacons guiding ships safely home. Long ago, when the first neutron star signals were detected, they opened an entirely new window onto the universe's most extreme physics. Today, gravitational wave detectors join this cosmic orchestra, listening for the space-time ripples created by neutron star mergers in distant galaxies. They're incredibly sensitive instruments ready to detect the whispers of cosmic violence transformed into scientific revelation, messages written in the very fabric of reality itself. Chapter 10: The Future of Neutron Stars. Neutron stars are among the longest-lived objects in the universe, with lifetimes measured in trillions of years. Long after our Sun has exhausted its nuclear fuel and faded to a dim white dwarf, long After all the stars in the galaxy have ceased their nuclear burning, neutron stars will continue their patient existence in the cosmic darkness. They are cosmic time capsules, destined to outlive virtually every other type of astronomical object except black holes, quietly spinning through an increasingly empty and cold universe. Picture the far future of the cosmos, perhaps 100 trillion years from now, when the last ordinary stars have burned out and the universe has entered what cosmologists call the degenerate era. In this distant epoch, neutron stars will be among the few remaining sources of energy in the universe, their rotation and magnetic fields still capable of powering faint emissions long after all other stellar processes have ceased. They will be lighthouses in a truly dark cosmic ocean, beacons of the universe's energetic past, persisting into its quiet future. Over millions of years, neutron stars gradually cool from surface temperatures of 1 million degrees to near absolute zero. This cooling process happens through several mechanisms: the emission of photons from the surface, the streaming away of neutrinos from the interior, and exotic cooling processes that may involve the creation of strange quarks or other exotic particles. The cooling follows a predictable pattern, allowing astronomers to estimate a neutron star's age by measuring its surface temperature through X-ray observations. The cooling process is beautifully gradual, like a cosmic ember slowly fading in the darkness. Young neutron stars glow brilliantly in X-rays, their surfaces hot enough to vaporize any normal matter that might approach too closely. Over millions of years, this thermal glow fades to infrared, then to radio frequencies, and eventually becomes undetectable by any conceivable instrument, leaving the neutron star as a cold, dark object visible only through its gravitational effects. The rotation of neutron stars gradually slows due to magnetic braking over millions of years. As the neutron star's magnetic field interacts with the sparse interstellar medium and the electromagnetic fields it generates, it experiences a gentle but persistent drag that gradually reduces its rotation rate. Young pulsars spinning hundreds of times per second eventually slow to periods of seconds or even minutes, their lighthouse beams sweeping ever more slowly across the cosmos until they finally fade below the threshold of detection. This magnetic braking process has a certain cosmic poetry, the very magnetic fields that make pulsars. Such brilliant beacons also serve as their eventual demise, gradually stealing their rotational energy and transforming dynamic young pulsars into sedate old neutron stars. The process spans millions of years, so slow that hundreds of human civilizations could rise and fall without detecting any change in a pulsar's rotation period. In the far future, neutron stars may eventually evaporate through Hawking radiation, but this process would take an unimaginably long time. Stephen Hawking's theoretical work suggests that even neutron stars should eventually emit radiation and slowly evaporate, though the timescale for this process is so vast, perhaps 10 to the power of 34 years, that it dwarfs the current age of the universe by a factor larger than the number of atoms in the observable cosmos. This evaporation would be so gradual that it would be essentially imperceptible even over trillions of generations. Some neutron stars will eventually collide with other neutron stars or black holes. Over the vast timescales of cosmic evolution, gravitational interactions can occasionally nudge neutron stars out of their stable orbits, sending them on collision courses with other compact objects. These future mergers will create brief flashes of gravitational waves and electromagnetic radiation, momentary bursts of energy. In an otherwise increasingly quiet universe, binary neutron star systems will continue to inspire gravitational waves as they spiral toward merger. The neutron star binaries we observe today are slowly losing energy through gravitational wave emission, their orbits decaying over millions or billions of years. In the distant future, these systems will finally merge, creating kilonova explosions that briefly illuminate the cosmic darkness and forge heavy elements that may never be incorporated into new stars or planets in the increasingly sparse universe of the far future. Neutron stars may serve as cosmic laboratories for studying fundamental physics throughout the universe's future evolution. As the universe continues to expand and cool, conditions elsewhere will become increasingly mild and ordinary, making neutron stars among the last remaining natural laboratories where matter exists under extreme conditions. Future civilizations, if they exist, may study ancient neutron stars to understand the physics of matter at nuclear density and the behavior of superfluids and superconductors on astronomical scales. The magnetic fields of neutron stars will gradually decay over cosmic time, but some may persist for billions of years. While most neutron star magnetic fields weaken significantly over millions of years, some may maintain substantial field strength for much longer periods. These long-lived magnetic fields could continue to accelerate charged particles and generate faint emissions even in the far future, creating whisper-quiet cosmic radio stations that persist long after all other sources of electromagnetic radiation have faded. Isolated neutron stars will eventually become invisible, dark stars, detectable only through their gravitational effects. After cooling below the threshold of thermal emission and slowing their rotation until their pulsar beams become undetectable, neutron stars will become essentially invisible to electromagnetic observation. They will persist as gravitational influences in the cosmic darkness, occasionally revealing their presence when they gravitationally lens the light from more distant objects or perturb the orbits of any remaining planetary bodies. Some neutron stars may capture dark matter particles, potentially providing future insights into the nature of dark matter. If dark matter particles can interact weakly with normal matter, neutron stars' intense gravitational fields may gradually accumulate dark matter in their interiors over cosmic time. This accumulated dark matter could potentially affect the neutron star's properties in ways that might be detectable by future astronomers, providing a natural laboratory for studying one of the universe's greatest mysteries. The universe's expansion may eventually isolate neutron stars from most other matter. As cosmic expansion accelerates due to dark energy, the average density of the universe will continue to decrease, and neutron stars will become increasingly isolated from other forms of matter. They will drift alone through an expanding, cooling cosmos, their gravitational influence extending only to their immediate vicinity in a universe that has grown vast and sparse. Future neutron star mergers will become increasingly rare as the universe evolves. As the supply of massive stars capable of creating new neutron stars gradually diminishes, and as existing neutron star binaries either merge or become unbound through gravitational interactions, the rate of neutron star formation and merger will decline. The spectacular kilonova explosions we observe today may eventually become cosmic rarities, occurring perhaps once per galaxy per billion years rather than once per 100,000 years. Neutron stars represent a bridge between the universe's energetic past and its quiet future. They are relics of an epoch when massive stars burned brightly and died violently, creating the heavy elements necessary for planets and life. In the far future, when star formation has ceased and the universe has entered its final phase of expansion and cooling, neutron stars will be among the last reminders of the cosmos' dynamic youth, spinning slowly in the darkness like cosmic time capsules preserving the memory of stellar death and rebirth. As you drift into the deepest reaches of sleep, imagine these neutron stars continuing their patient journey through cosmic time, outlasting civilizations, galaxies, and perhaps even the protons from which they were originally formed. Over vast stretches of time that dwarf human comprehension, they will slowly cool and fade, their rotation gradually slowing until their pulsar beams no longer sweep across space with detectable intensity. Even now, in the quiet darkness of your rest, neutron stars throughout the universe continue their ancient dance, spinning through the cosmic night with a patience that measures time in billions of years. They are monuments to the universe's capacity for creating objects of incredible stability and longevity, from moments of spectacular stellar death, cosmic lighthouses that will continue their quiet vigil long after the last star has burned out and the universe has settled into its final, peaceful equilibrium. In the end, neutron stars teach us about permanence and change, about how the universe creates lasting beauty from temporary violence, and about the incredible scales of time over which cosmic evolution unfolds. They remind us that even in a universe destined for increasing emptiness and cold, there will always be these patient sentinels, spinning slowly through the darkness, carrying within their dense cores the compressed history of stellar lives and deaths, the distilled essence of cosmic evolution preserved in forms so stable they approach eternity itself. Closing section. As our gentle journey through the mysteries of neutron stars draws to its peaceful conclusion, take a moment to reflect on the incredible voyage we've shared together through these cosmic lighthouses. We've explored objects so dense that cities could fit within them yet contain more mass than our sun, witnessed magnetic kingdoms that extend millions of miles into space, and contemplated collisions that forge the very elements from which planets and life itself are made. These stellar remnants, born from the quiet transformation of dying suns, represent some of the universe's most extraordinary achievements, cosmic laboratories where matter exists in states so exotic they challenge our understanding of reality itself. From their crystalline crusts harder than diamond to their superfluid cores where quantum mechanics operates on astronomical scales, neutron stars bridge the gap between the microscopic world of particle physics and the vast scales of astronomical objects. In contemplating these ancient objects, spinning patiently in the cosmic darkness for millions of years, we find a profound sense of perspective about our place in the universe. The atoms in your body, the gold in your jewelry, the iron in your blood, all were forged in stellar furnaces and scattered into space by the very processes that create neutron stars. You are intimately connected to these distant stellar remnants. Through the shared history of cosmic evolution, participants in a story that spans billions of years and countless generations of stars. As you rest now in comfortable darkness, remember that somewhere in our galaxy, radio telescopes continue their patient listening, detecting the precise timing of pulsar signals that serve as cosmic clocks, more accurate than any human timepiece. Gravitational wave detectors stand ready to sense the space-time ripples from distant neutron star mergers, while X-ray telescopes observe the hot gas spiraling onto neutron stars in binary systems, each observation adding to our understanding of these remarkable objects. The universe reveals its deepest secrets gradually, through careful observation and patient study, much like the slow process of drifting into peaceful sleep. Each new discovery about neutron stars opens additional questions, creating an endless frontier of cosmic mystery that will engage human curiosity for generations to come. These objects remind us that the cosmos is far stranger and more wonderful than our everyday experience suggests, filled with phenomena that stretch our imagination and challenge our understanding of what is possible. In your dreams tonight, you might find yourself drifting through the gentle magnetic kingdoms surrounding these stellar remnants, witnessing the slow cosmic ballet of binary neutron stars as they spiral together over millions of years, or standing on the impossibly smooth surface of a neutron star, looking up at a sky where distant galaxies appear as mere points of light in the cosmic darkness. Tomorrow, when you wake, the neutron stars will still be there, continuing their ancient rotations with clockwork precision, their lighthouse beams sweeping across the galaxy, their magnetic fields sculpting invisible architectures of force in the vacuum of space. They will be there next week, next year, next century, spinning with a patience that measures time in geological epochs rather than human lifetimes. If tonight's journey into the mysteries of neutron stars has brought you peace and wonder, you might enjoy our upcoming exploration of the cosmic web, where we'll discover how galaxies are connected by invisible filaments of dark matter spanning hundreds of millions of light-years, creating the largest structures in the observable universe. Until then, rest well under the gentle light of distant stars, knowing that you've touched something of the eternal through our shared exploration of these magnificent cosmic monuments. Let the knowledge of neutron stars carry you gently into sleep, these stellar lighthouses continuing their quiet vigil in the depths of space, spinning slowly through the cosmic night, preserving within their dense cores the compressed wisdom of stellar evolution, the patient secrets of matter under extreme conditions, and the enduring beauty of physical laws operating on scales both unimaginably small and inconceivably vast. Sleep well, cosmic traveler, and dream of neutron stars.